She's a super smart programmer, author, and senior lecturer at MIT. Her computer science videos on our channel have captivated millions of learners around the world. Today we talk about Python, growth mindset, and rubber ducks. I have to know what the ducks are now. I can't continue. And I ask her, with the emergence of AI, do we even still need to learn how to code? What's the value proposition of learning a language like Python? Do we still need to do it?
So, not sure if this exactly answers the question.
Oh, tell me more. Find out her answer today on Chalk Radio. Hi, Anna.
Hi, how are you?
I'm good. You're here.
Yes.
I'm so excited.
Yes, you too.
This is one of our pilot episodes for something new that we're trying, which is a video version of our Chalk Radio podcast. In many ways, it's an experiment. How do you feel about experiments? Are you an adventurous person?
No, not at all.
Oh, great. We're going to be great.
Yeah, I like stability and I like boring days.
Oh, well, I'm not sure we're going to have one of those with these ducks.
That's
and
right.
So I actually don't know what the ducks mean.
Yep.
So I think you're going to tell me a little bit later. But I think we're in for an adventure and a little bit maybe of a choose your own adventure.
Mm-hmm.
So you're at MIT. You've been here for about 10 years. And you spend most of your time thinking about and teaching people who are new to programming, introducing them.
Yes.
And I'm wondering what that means to you, why you're interested in teaching, in particular, like people like me. What do you get out of that? And tell me about that experience.
So I recognize that I don't want everyone to become a computer scientist, but I do think that everyone should learn programming as a skill. So programming should become sort of like what math is now, where you kind of learn it in elementary school, and you obviously use it here and there in your adult life, but I don't know, when you've last used calculus, right? Like, we don't all need to become mathematicians after we've learned basic math. Similarly, I do think people should learn basic programming, but they don't have to become computer scientists. So the reason that I enjoy teaching students intro programming and exposing them to intro computer science is because it was really hard for me to understand programming when I first started, and I just always remember how tough it was. And I teach at MIT, and there's obviously a lot of really smart people here, and I think as you teach more and more, it's easy to forget how hard it was to start learning. And so, as an intro course, you might make the problems you give students harder and harder each year just because they get maybe boring for you, but it's not boring for the students. And I try to recognize that every semester. I just remember it was really hard for me. They've never seen this before. So it's really important to make sure that they have a really good experience.
You mentioned that when you first started programming, it was difficult.
Yep. I'm
wondering, what made it difficult? And then what are you doing in your teaching to make it less difficult?
I honestly don't know what made it difficult. The beginning was easy, just kind of understanding the basics of just, writing. The basics of creating an algorithm is basically three things. So the first is a sequence of steps. So step 1, step 2, step 3. Some sort of way to control the flow of those steps. So usually you go step by step, but at some point you say, well, if this is true, do this, otherwise do this. So like a branching kind of idea. And then there's also a way to control the flow by asking the program to repeat certain lines. So it's like, well, if this is true, go back and repeat this 1,000,000 times, which is very easy for a computer to do. So a sequence of steps, a way to control the flow of those steps, and then a way to stop. Those are the three things that make an algorithm. That's how you write a program. And grasping that was not hard. It was just sort of once you've gotten over that learning curve, it's learning sort of some of the more advanced concepts that were harder, some of the details for how that specific language works. So I started with Java, not Python, which was it's a lot harder than Python. There's a bunch of details that you need to think about there.
So I had the opportunity to watch some of your lecture videos.
Oh, great.
Yeah. And I noticed that you make space and time for students to practice, right in the class itself.
Definitely, yes.
Outside the class as well, but in the actual space where you're teaching. And I'm wondering if you could talk about that a little bit, why you do that.
Yeah, so I think I mentioned this before. I sort of see programming like math is now, but this will be, many years from now. It's a skill that people need to get that they don't have yet. And so if we think about the way we learn math in school, it's a lot of practice, right? You just always constantly practice adding, subtracting, multiplying, right? The kids. Yeah. So I think it's very important for students to actually get the time to do that practice. The way I run the class is a sort of a flipped classroom or a blended learning style where students watch sort of the basics through video first. And then in the actual classroom, we do active learning. So I go over maybe something that's a little bit more confusing, and then I give them time to break with the hope that me forcing them to have them actually start coding, they'll be able to see, I totally understood what she was talking about in the video, and I can totally code that. But then when I'm forcing them to actually do it, starting with a blank slate, it's pretty daunting. And so I want them to get over that bump where it's like you have a blank piece of, blank editor or whatever, and then you just have to start writing something down. The more you do it, the more you feel comfortable with it. Mm-hmm. So there's all these breaks for all these activities that I try to keep the class lively, of course, and and kind of indirectly have them practice these skills, like just write something down.
Yeah, and also that does two things, I think. It de-emphasizes perfection. You're like, this is practice. Like, yep. I think like an artist, right? So just like get a sketch, write a few lines, like just get something down.
Yes.
And then we can improve it.
Yep.
And then that speaks to something else you've mentioned before, and that's like growth mindset, and that programming is not like a gift and you have it or you don't, but it's really something that can be developed.
Yeah, a lot of, you see some people who are really good at programming, they didn't get good just because they had that skill. They were born with it, right? There's a lot of growth mindset involved in that. And anybody can reach that level of being good at something, programming included, just by lots of practice, trying different things, challenging themselves. So not just sticking to things that are obviously way too easy, because then you'll never grow. But you kind of, like, I don't know if you know this, the state of flow. It's like this chart where you kind of want to be in this like middle band, but kind of oscillating between doing things that are too easy and then challenging yourself and doing things that are a little bit harder. You don't want to always do two things too hard, because then that's discouraging and you'll stop. But you don't want to do things that are always too easy, because then you'll never grow.
I wonder if we could write an algorithm for staying in the flow.
Yes.
Like it tracks like, this is too easy for you.
Yeah, so
like get in another...
a lot of the education platforms, right, are trying to give students, based on their responses, even in math questions, right, they'll be like, this student totally got all these, let me give them a harder one. And it's like, that was too hard, let me...
Yeah. How did you find your way to programming? Is this something that you've always wanted to do, or did it develop along the way?
So my parents immigrated from Romania, and we immigrated to Canada, and my dad was an electrical engineer, and then he went into software engineering. And being an immigrant parents from Europe, we were highly encouraged, my sister and I were highly encouraged to get some sort of engineering job, right? So it's just what is done. And so computer engineering or computer science, something along those lines, seemed to be the best option, given sort of where things were going in the future. This was the 90s. So just the beginning of the internet, the beginning of all that, right, that boom. So my dad recognized that was sort of what the future would be. And he said, you should probably learn to program and potentially probably go into that sort of career. And I wasn't super interested in anything else, so I just said, sure. And so he taught us Java when I was about 12. I have a picture here.
Yeah, let's see it.
Okay, and it's in this really cool frame.
Oh, I love that frame.
Okay, very fitting. And so this is very 90s, Right?
I love
this
everything
exudes
about it.
90s.
Yes.
Peak 90s right there. So we've got the room with the computer, right? Like as was in the 90s, you all had like the room with the computer.
Yes.
And then like the big chair and the side ponytail or whatever. That's me
the
on
scrunchies.
the left there. That's me. Yep. And that's my sister on the chair, sitting on the chair.
Yeah.
And that's when we first, or maybe before, like very close to the time that we had first started programming. My dad just said, here's some really basic things. And then I only got to the if, like the branching part of the control flow. I didn't really get to the repeating part of the control flow. So I made this choose your own adventure program where it was like, I forget what it was, like get out, exit a castle or whatever it was. And it was just like a bunch of if, else, if, else, if, else, if, else, if, like something like that. It looked really ugly, but I had a lot of fun doing it.
But in a way, you're helping people choose their own adventure today through programming, like gaining independence, critical thinking, doing things that they rely on other people to do, like they can do themselves. Like that's kind of incredible that you do that.
It's pretty fun. That's what I get out of it. Like I said, I don't want people to become computer scientists. I just want to empower them to, I don't know, like if they want to make their own app, they can totally do that using really basic computer science skills or programming skills, not necessarily computer science skills, but yeah.
So, controversial question. I asked you before the show a question, and I have not seen the answer yet.
Okay.
But the question was, in an environment when there are coding tools out there that allow people to build things, what's the value proposition of learning a language like Python to do that? Like, do we still need to do it? And what's the value proposition of doing it? So you're going to reveal your answer.
Okay, I'll reveal my answer. So, not sure if this exactly answers the question, but I said trust but verify.
Oh, tell me more.
Okay, yeah, I've definitely used GenAI tools before. And even for really simple things, it can get it wrong, especially mathematical things and even programming things. And so I have sort of I would say a basic knowledge of programming. And I
have to interrupt you. I would say it's a little more than basic for everyone out there. More than basic. Continue.
And so I was able to start with what GenAI gave me as a program, and kind of tell, you know what, in this particular test case, it doesn't really work that well. And I didn't have to go back and ask it to fix it, because that requires a lot more sort of back and forth with prompting. And I was able, to just fix it on my own. It wasn't that hard of a fix. And, as soon as you go back and prompt the GenAI again and again and again, you start to introduce sort of variability of English language, right? Like when you're talking to someone online, it's really hard to tell what they mean, or, right, there's all these double meanings. And GenAI is all probabilistic. So they're basically going to, pick the highest probability of what you mean. And then when they give you answers back, again, they give it to you with whatever the highest probability for the next word to be. That's what they spit back at you. So as soon as you introduce sort of that prompting back and forth, it can introduce errors that potentially stack on top of errors, misunderstandings, and things like that. So having a really basic knowledge of programming could allow you to maybe start with a piece of code that the GenAI gives you back. So you're not starting with a blank slate. It's not super daunting to write it yourself, but you start with something and then you potentially test it and then debug it and then, figure it out. Okay, now I trust that it works well. Yeah.
I feel like the ability to verify is the human component.
Yes.
And that is sort of what creates the balance with AI. Like if you let AI make all the decisions, then you've lost your self-reliance, and you can't choose your own adventure because you're going to get a bunch of errors and it's going to lead you down the wrong path. So you need the knowledge to be able to choose a path that makes sense. Yeah. I have to know what the ducks are now. Like I can't continue. So
okay.
And a pig. And is that like noisy data, or
this is not noisy data?
Okay.
So every semester when we run our classes on Intro to Programming and Computer Science, there is one particular class that is on debugging.
Okay.
Which is the process of, you wrote a piece of code,
right,
and it's not running as you expect it to. So how do you fix it? That is the debugging process. And so a lot of times, a bunch of the errors might be things that you can easily fix, but most of the time, your program runs fine and it gives you an answer, but the answer is not what you thought it should be. That's kind of where programming is kind of different than English, for example, because in English, if you write a sentence, somebody else can interpret it however they'd like. Like one example we give to students is the chicken is ready to eat. What do you think about when I say the chicken is ready to eat?
Well, I'm a vegetarian, so I don't want to actually eat the chicken, but I would, because I'm a vegetarian, I assume the chicken wants to eat his food.
Okay. There you go. But I would assume I enjoy meat. So, my take on that is I have a chicken on the table and I'm going to eat it. Right. So there's two interpretations to that. But when we write code, there's only one way to interpret that piece of code that is written. Right. So that's where things go wrong in our code because we're like, well, it should work because in my mind, when I kind of thought about it, it's supposed to give me the right answer, but it doesn't, right? And so obviously the program is the one who's wrong because the computer is merely following the algorithm, the set of instructions, and there's only one way to follow those instructions. That's basically what that whole class is about. And then I bring out this big box of ducks and I say, programming is actually kind of creative because the solution to a problem, you could brute force a bunch of things, but oftentimes the solution to a debugging problem is just to take time away from it and then potentially explain exactly what you think the code is doing to someone who knows absolutely nothing about programming. Oh. It could be you.
Yes, I'm available.
Or it could be a rubber duck.
Oh.
So this is called rubber ducky debugging because it's an inanimate object that doesn't know anything about programming.
Right.
And it forces you to scrutinize every single line of code that you wrote, even ones you think are correct. Most often, it's the ones that you think are correct that kind of are the issue. It's kind of like, where did I put my glasses, right? And you spend a long time looking for them and they're on top of your head. Yep. It's that exact feeling. It's like, where is that error coming from? And it's going to be something super simple. So the rubber duck is what helps you figure that problem out because you're explaining it in very grave detail to something that doesn't know. And if ducks are not your thing, there are frogs
and
pigs.
Of course.
Or friends, if you want to explain it to them.
But friends can be judgy.
Friends can be judgy. Yes. Yeah. So I used to explain my code to my son when he was 1. Yeah. When I had issues because he doesn't know anything about programming.
Right. And so it's the act of talking it through. But you said it has to be in great detail.
Yes, you can't skip because because you already, clearly your code is wrong because of you. And so, and so don't skip any details, right?
I feel like this is very much like life outside of academia.
Yeah.
90% of the time, the problem is probably you, and it's you have to figure out how to interact in the world or with others.
Totally. So I brought all these ducks, a wide variety. Yeah. So now I have a question for you. Uh-oh. Which duck would you like to keep? This is a hidden personality test.
Oh.
No, it's not.
We'll probably have to cut this because it might take a long time. I would, this guy. This guy. Yeah. He's a little bit offbeat.
Yeah.
Eye-catching. And I feel like I could explain stuff to him. Yeah. I get to keep him?
Yeah, of course.
Thank you. That's so great.
And you put one for the set as well.
Really? Yeah. Oh, gosh. Does someone from the crew want to, pick a duck for the set?
You took the one I would have picked.
Oh no.
All right, then.
There's another Mohawk guy right over there.
Yeah. We'll go 2 Mohawks.
There you go.
Thank you.
Yeah, of course.
What a gift.
So you can use it for programming if you decide to start, or as you said, and even in your day-to-day life, you can, if you just explain the problem to, something that doesn't judge or.
Yeah. This idea of taking a break.
Yes.
The process of programming itself seems quite intense. There's an image in popular culture of a person working alone in the dark, like with a hoodie and like tap, 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 for hours on end. Like that sounds intense. So there's two pieces. Like, is that accurate? And two, like, do people work in isolation like that, or is it more collaborative?
So I tend to encourage collaboration.
Okay.
I have certainly put a hoodie on and the hood on in the past, just like a leave me alone kind of state, mostly for, homework and things like that. But for students learning to program, I definitely encourage collaboration because it's when you talk to somebody else, you kind of see their viewpoint. And in programming, I know I talked about like an algorithm, but for a particular algorithm or even just to solve a specific problem, there's a ton of ways to solve it. So I learn from in the classroom when I ask students for how did they solve a particular problem after I give them some time to think about it, they have so many different approaches to it that I would never have thought of. And it's important for students to see all these different approaches because my way might not be the way that they think to approach the problem. So I encourage kind of working together, especially as you're learning. Now, after you find your groove, maybe it's not necessary, but.
Yeah, as an outsider to this, I didn't realize there was such room for divergent thinking. So that's really cool.
Yeah.
But the taking a break, so especially at a place like MIT, like I don't know if like taking a break is on the menu, really. But it should be, I'm guessing.
It should be, yeah.
And then I'm wondering if you can talk to us about like the thing you created in the world to help people take a break and why it's important.
Sure. So this was a project I just had an idea. I was like, let me just make a coloring book. One of those coloring books that you just kind of doodle into. Yeah. And I thought, let me just make it computer science themed. And so each one of these is, like, here's a circuit and it's like, here's a network, right, of connected people. And then here's a matrix kind of thing, right, with bits. And so it was just kind of all these ideas from computer science. And the hope is that if you are stuck and you don't have a duck,
right, then
you can take a coloring book. It doesn't have to be this one, but just something that gives your brain a break. But it's this idea of mind wandering. And this is an idea from psychology where mind wandering is not bad. Like if you're folding laundry, right, you're doing a very repetitive task. Your brain doesn't have to super focus on it. And so that's when inspiration comes because you're kind of subconsciously thinking about other things, maybe problems that you have or, things that you're worried about. And that's kind of when solutions come, just like, when you're taking a shower, that's mind wandering as well because you're doing a task that you already know how to do. You don't need to dedicate any thought to it. So your brain kind of dedicates thought to other things that might be worrying you or on your mind.
That's great that you've created that. Do you feel like programming is, what's the percentage of logic to creativity when it comes to programming? Are we like 50-50, 80-20,
Interesting.
60-40?
Maybe 50-50, I would say. I think creativity comes into the process at all the different levels. So when you're coming up with a problem or something that you want to solve using programming, right, you have to be creative, right? So just coming up with that is mostly creativity. When you're deciding how to solve the problem or how to write the code, sort of maybe what algorithm to use or how to structure it or like what pieces to use and where, that requires some creativity, potentially, putting things together that you might not have put before, pieces of programming concepts together that you might not have put before. And then you're obviously going to run into an error after you write the code the first time. Yeah. And so then tons of creativity comes into play there. With, drawing or talking to a duck.
I'm liking programming more and more, I have to say.
I don't know. Once you're programming, it's kind of like reading a really good book. Like you're in this Zen space where you're just like, yeah, this is working. Like I totally see where this is going. Like I know what I want to write next. Like the code just kind of fits together. So just like being in a good book is awesome. Wow. And then the more you program, the more you want to program because you're just gaining these skills along the way. So it's like you're like I play video games, so, you're just constantly like looking for new ways to level up, but there's no cap.
It's really fascinating because unlike video games, most of them, like you could use open source coding languages and financial barriers don't come into play to get that area for growth and that dopamine hit of like leveling up. Increasing your skills.
It's just kind of a different, like you said, it's a growth mindset, right? It's a different way of it's different fun.
It's a different fun.
It's a different fun.
I'm like more and more, I'm like, maybe I want to try this fun.
Well, there's a book right here.
Get Programming, Learn to Code with Python.
Yeah, so this I wrote a while ago. It's a book made, lots of things claim to be for beginners, but I wanted to write something that is actually for people who have never programmed before. So I think we don't even get into writing code to like chapter 7 or something like that. It's mostly kind of just setting up motivation, but not boring. Like I wanted it to read like a novel, right? Like you're just like, I'm just following along. So if you want to start, you could also, you could try this book. You can keep this copy.
Oh my gosh, I have to tell you a secret.
Yes.
So I requested this through interlibrary loan at my home library. And I asked one of my family members to pick it up. And I was like, just so you know, it's really for me. Like, because they would be like, why is she getting this book? This must be the wrong thing. I was like, it's not a mistake. Like, it's actually for me. But I didn't really believe that. But now I feel like it is for me.
Oh, great.
Like, I do want to read it now and learn.
Yeah, anybody can start for sure.
Yeah, that's just great. Do you have any like hot tips for newbies who might want to start, or even people who are like deep into programming, deep into the hoodie already? Like things you're interested in reading or you think other people should view or listen to start or continue their journeys? Mostly tips for
newbies, I would say.
Okay.
Don't get discouraged. Learning curve is steep.
Yeah. Okay.
Yeah. It sucks. But
can I text you when I...
Yes, you can text me.
Thank you. If the duck doesn't work.
If the duck doesn't work, yeah. No, you're learning a new language. Like, it's called a programming language, right? And it's basically learning a new way to write things that you already know how to do or how to write in English.
Yeah.
You're just structuring it in a completely different way in a different language. So the learning curve is steep, but don't get discouraged. With GenAI tools now, though, it's easy to get started, right? That's not from scratch. So like I mentioned earlier, if you're stuck on a problem, just prompt it to give you a solution and then work on the trust but verify piece where you'll actually get valuable experience debugging, right? Because you already start with a piece of code. So like the confidence level is already kind of there. You're like, okay, I'm not starting blank. And then you can, try to fix it or agree that it works. And both are really valuable skills to practice as beginner programmers.
I love the idea of starting with code and practicing debugging.
Yeah.
That feels like low stakes and doable.
Totally.
Yeah. What have I not asked you that I should have asked you?
I want to know what games.
What games
you play?
Oh my gosh. Like video games?
Yep.
I like driving a lot, so I drive in the real life.
Wait, you do not. You said you don't like being stuck in traffic.
No, I don't like being stuck, so I like to drive.
Oh, I see.
So I also enjoy driving games.
Okay.
Not just around the track, but like through random city streets and things like that. Escaping the police and, like the usual.
You have a whole other side to you.
Like Need for Speed?
Like GTA. Yeah.
Okay,
GTA played, Need for Speed, yeah. I have the setup with the wheel and
Oh, wow. Well, thank you so much for being here. I learned about myself. I learned about programming. I have a whole new worldview on what is possible with and through programming, and that's just an incredible gift. And I'm so glad we get to share that with a lot of people who might also take that gift and run with it. So thank you.
It's awesome. Glad to hear. Thank you for the chat. This was awesome.
And thank you for the duck.
Yes.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right, everyone, let's get started. So, today's lecture and Wednesday's lecture, we're going to talk about this thing called object-oriented programming. And if you haven't programmed before, I think this is a fairly tough concept to grasp. But hopefully with many examples and just by looking at the code from available from the lectures, you'll hopefully get the hang of it quickly. So, let's talk a little bit about objects. And we've seen objects in Python so far. Objects are basically data in Python. So every object that we've seen has a certain type. Okay, that we know. Behind the scenes, though, every object has these two additional things. One is some data representation, so how Python represents the object in just behind the scenes. And what are different ways that you can interact with the object. Okay. So for example, every one of these is a different object. For example, this is the number 1234. It's a specific object that is of type integer. The number 5 is a different object that's of type integer, and so on. We've seen floats, we've seen strings, we've seen lists. Lists and dictionaries are more complicated object types, sorry. But every object has a type, some sort of way that it's represented in Python, and some ways that we can interact with them. Okay, so the idea behind object-oriented programming is, first of all, everything in Python is an object. We've said that before, and in this lecture, I think we'll really get at what that means. So we've seen strings, integers, dictionaries, lists, those are all objects. When we did functions, we saw that we could pass as a parameter another function, so functions were also objects in Python. So literally everything in Python is an object. So what are the kinds of things we can do with objects? Well, once you have a type, you can create a new object that is of some type, and you can create as many objects as you'd like of that particular type, right? An integer 5, an integer 7, those all work in a program. Once you've created these new objects, you can manipulate them. So for a list, for example, you can append an item to the end of the list. You can delete an item, remove it, concatenate two lists together. So that's ways that you can interact with objects. And the last thing you can do is you can destroy them. So with lists, we saw explicitly that you can delete elements from a list, or you can just forget about them by sort of reassigning a variable to another value, and then at some point Python will collect all of these dead objects and reclaim the memory. So let's continue exploring what objects are. So let's say I have these two separate objects. One is a blue car, one is a pink car. So objects are really data abstractions. So these two cars can be created by the same blueprint. Okay? This is a blueprint for a car. And if an object is a data abstraction, there's two things that this abstraction is going to capture. The first is some sort of representation. What is going to represent the car? What data represents a car object? And the second is, what are ways that we can interact with the object? So if we think about a car blueprint, some general representation for a car could be the number of wheels it has, the number of doors it has, maybe its length, maybe its height. So this is all part of what data represents the car. Okay? The interface for the car is what are ways that you can interact with it. So for example, you could paint a car, right? So you could change its color. You could have the car make a noise, and different cars might make different noises. Or you can drive the car, right? So these are all ways that you can interact with a car. Whereas the representation are what makes up the car, what data abstractions make up the car. Let's bring it a little closer to home by looking at a list. So we have this data type of list, right? We've worked with lists before. The list with elements 1, 2, 3, and 4 is a very specific object that is of type list. Okay? Again, we think about it in terms of two things. One is what is the data representation of a list? So behind the scenes, how does Python see lists? And the second is, how do you interact with lists? So what are ways that you can manipulate a list object once it's created? So behind the scenes, you have a list L, which is going to be made up of essentially two things. One is going to be the value at specific index. Okay? So at index 0, it has the value 1, right? Because it's the first element in the list. And the second thing that represents a list is going to be this second part, which is a pointer. And internally, this pointer is going to tell Python where is the memory location in the computer where you can access the element at index 1. So it's just essentially going to be a chain going from one index to the other. And at the next memory location, you have the value at index 1, and then you have another pointer that takes you to the location in memory where the index 2 is located. And at index 2, you have the value, and then the next pointer, and so on and so on. So this is how Python internally represents a list. Okay? How you manipulate lists, we've done this a lot, right? You can index into a list, you can add two lists together, you can get the length, you can append to the end of a list, you can sort a list, reverse a list, and so many other things, right? So these are all ways that you can interact with the list object as soon as you've created it. So notice both of these, the internal representation and how you manipulate lists, you don't actually know internally how these are represented, right? How did whoever wrote the list class decide to implement a sort? We don't know. Okay? You also weren't aware of how these lists were represented internally. And you didn't need to know that. That's the beauty of object-oriented programming and having these data abstractions. The representations are private of these objects, and they're only known by, well, you can find out how it's done, but they only should be known by whoever implemented them. Right? You, as someone who uses this class, doesn't really need to know how a list is represented internally in order to be able to use it and to write cool programs with them. Okay, so just final motivation here before we start writing our own types of objects is the advantages of object-oriented programming is really that you're able to bundle this data, bundle some internal representation and some ways to interact with a program into these packages. And with these packages, you can create objects. And all of these objects are going to behave the exact same way. They're going to have the same internal representation and the same way that you can interact with them. Okay? And ultimately, this is going to contribute to the decomposition and abstraction ideas that we talked about when we talked about functions. And that means that you're going to be able to write code that's a lot more reusable and a lot easier to read in the future. Okay. So, just like when we talked about functions, we're going to sort of separate the code that we talk about today into code where you implement a data type and code where you use an object that you create. Okay? So remember when we talked about functions, you were thinking about it in terms of writing a function, so you had to worry about the details of how you implement a function. And then you had to worry about just how to use a function. Right? So it's sort of the same idea today. So when you're thinking about implementing your own data type, you do that with this thing called a class. Okay? And when you create a class, you're basically going to figure out what name you want to give your class, and you're going to define some attributes. And the attributes are going to be the data representation and ways that you can interact with your object. So you, as the programmer of this class, are going to decide how you want people to interact with your object and what data this object is going to have. So for example, someone wrote code that implements a list class, right? And we don't actually know how that was done, but we can find out. So creating the class is implementing the class and figuring out data representation and ways to interact with the class. Once that's done, you can then use your class. And you use the class by creating new instances of of the class. So when you create a new instance, you essentially create a new object that has the type, the name of your class. And you can create as many objects as you'd like. You can do all the operations that you've defined on the class. So for example, someone wrote the code to implement a list class, and then you can just use the list class like this. So you can create a new list. You can get the length of the list. You can append to the end of the list, and so on and so on. OK. So let's start defining our own types. Okay? So now you're going to define classes. You're going to write classes which are going to define your own types of objects. So for today's lecture, we're going to look at code that's going to be in the context of a coordinate object. Okay? And a coordinate object is essentially going to be an object that's going to define a point in an xy plane. Okay? So x comma y is going to be a coordinate in a 2D plane. So we're going to write code that's going to allow us to define that kind of object. So the way we do that is we have to define a class. So we have to tell Python, hey, I'm defining my own object type. So you do that with this class keyword. So you say class. Then you say the name of your type. In this case, we're creating a type called coordinate. Just like we had type list, type string, and so on, this is going to be a type called coordinate. And then in parentheses here, you put what the parents of the class are. For today's lecture, the parent of the classes are going to be this thing called object. An object is the very basic type in Python. It is the most basic type in Python. And it implements things like being able to assign variables. So really, really basic operations that you can do with objects. Okay? So your coordinate is therefore going to be an object in Python. All right, so we've told Python we want to define an object. So inside the class definition, we're going to put attributes. So what are attributes? Attributes are going to be data and procedures that belong to the class. Okay? Data are going to be the data representations, and procedures are going to be ways that we can interact with the object. Okay? The fact that they belong to the class means that the data and the procedures that we write are only going to work with an object of this type. Okay? If you try to use any of the data or the procedures with an object of a different type, you're going to get an error. Because these objects, this data and these attributes, will belong to this particular class. Okay? So the data attributes is what is the object, right? What is the data that makes up the object? So for our coordinate example, it's going to be the x and y values for a coordinate. We can decide they can be ints. We can decide that we can let them be floats. But it's going to have one value for the x coordinate and one value for the y coordinate. So those are data attributes. And procedural attributes are better known as methods. And you can think of a method as a function, except that it's a function that only works with this particular type of object. So with a coordinate object, in this case. Okay? So the methods are going to define how you can interact with the object. So in a list, for example, we've said that you can append an item to the end of the list. We can sort a list, things like that. So when you're defining methods, you're defining ways that people can interact with your object. So for example, for a coordinate object, we can say that we can take the distance between two coordinate points. Okay? And that's going to be a way that you can interact with two coordinate points. And just to be clear, these are going to belong to this class, which means that if you try to use this distance method on two lists, for example, you're going to get an error. Because this distance method was only defined to work with two coordinate type objects. All right, so let's carry on and continue implementing our class. So we've written this first line so far, class coordinate object. So now let's define attributes. First thing we're going to define are data attributes. And generally, you define data attributes inside this init. And this is underscore underscore init underscore underscore. And it's a special method or function in a class. And the special method tells Python when you implement this special method, it tells Python, when you first create an object of this type, call this method, or call this function. So how do we do that? So let's implement it. So you say def, because it's just a function. The name is the special name init. And we give it some parameters, right? Just like any other function. These last two parameters are x and y, which are going to represent the x. It's going to represent how you create a coordinate object. So you give it a value for the x coordinate, and you give it a value for the y coordinate. The self, however, is a little bit trickier. So the self is going to be a parameter, when you define this class, that represents a particular instance of the class. Okay? So we're defining this coordinate object in sort of a general way. Right? We don't have a specific instance yet because we haven't created an object yet. But this self is going to be sort of a placeholder for any sort of instance when you create the object. So in the definition of the class, whenever you want to refer to attributes that belong to an instance, you have to use self dot, so this dot notation. And the dot is going to say, look for a value x, look for a data attribute x that belongs to this class. Okay? So for methods that belong to the class, the first parameter is always going to be self. It could be named anything you want, but really by convention, it's always named self. So try to stick to that. And then any other parameters beyond it are going to be just parameters as you would put in a normal function. Okay? In this particular case, we're going to choose to initialize a coordinate object by two values, one for the x and one for the y. And inside this init method, we're going to have two assignments. The first one says the x data attribute of a coordinate object. I'm going to assign it to whatever was passed in. And the y data attribute for a particular object is going to be assigned whatever y was passed in. Questions so far about how to write this init? Yeah, question. How do you make sure that x and y are ints or floats? So this is something that you could write in the specification, so the docstring with the triple quotes. So whoever uses the class would then know that if they do something outside the specification, the code might not work as expected. Or you could put an assert statement inside the definition of the init, just to sort of force that to be true. Great question. Yeah, question. Does this self x and this x have to be the same name? The answer is no. And we're going to see in the class exercise that you can have it to be different. Okay, great. So this defines the way that we create an object. So now we have sort of a nice class. It's very simple, but we can start actually creating coordinate objects. Okay? So when you create coordinate objects, you're creating instances of the class. So this line here, c is equal to coordinate 3, 4, is going to call the init method. It's going to call the init method with x is equal to 3 and y is equal to 4. I'm just going to go over here. And I wrote this previously because notice when we're calling this method, when we're creating an object here, we're only giving it 2 parameters. But in the init method, we have actually 3 parameters, right? We have these 3 parameters here. But when we're creating an object, we only give it 2 parameters. And that's OK, because implicitly, Python's going to say self is going to be this object c, so just by default. Okay? So when you're creating a coordinate object, you're passing it all the variables except for self. So this line here is going to call the init, and it's going to do every line inside the init. So it's going to create an x data attribute for c, a y data attribute for C, and it's going to assign 3 and 4 to those respectively. This next line here is origin equals coordinate 0, 0, creates another object, okay? It's another coordinate object whose value for x is 0 and whose value for y is 0. Okay, so now we have 2 coordinate objects. We can access the data attributes using this dot notation, and we've seen that before, right? When we've worked with lists, we'd say something like l.append, right, when we create a list. So the same dot notation can be used with your own objects in order to access data attributes. So here, this is going to print 3 because the x value for object C is 3. And the next line, print origin x, is going to print 0 because the x value for the object origin is 0. Okay, so we've created a coordinate object. We've defined the init method, so we have a way to create objects when we use the class, and then we can access the data attributes. But that's kind of lame, right? Because there isn't anything cool we can do with it. There isn't ways to interact with this object. So let's add some methods. Okay, remember, methods are going to be procedural attributes that allow us to interact with our object. Okay? Methods are like functions, except that there's a couple differences which you'll see in a moment. And when you're calling methods, you're using the dot operator, like l.append, for example, for lists. So let's go back to defining our coordinate class, and let's define a method for it. So far, we've defined that part there, class coordinate and an init. So we have that. So in this slide, we're going to add this method here. So this method here is going to say, I'm going to define a method called distance, and I'm going to pass in 2 parameters. Remember, self, the first parameter, is always going to be the instance of an object that you're going to perform the operation on. So pretty much by convention, it's always named self. Okay? And then for this particular method, I'm going to give it another parameter, and I can name this whatever I want. I'm naming it other. And this is going to represent the other coordinate object for which I want to find the distance from myself. Okay? So here I'm going to just implement the Euclidean distance formula, which is x1 minus x2 squared plus y1 minus y2 squared and square root of all that. So that's what I'm doing inside here. Okay? Self and other are coordinate objects. Inside this method, I have to refer to the x data attributes of each object if I want to find the difference between the 2 x values from them. So that's why I'm doing self.x here, right? If I just did x, I would be accessing just some variable named x in a program, which actually isn't even defined, right? So you always have to refer when you're talking about as we're thinking about classes, you always have to refer to whose data attribute do you want to access. Okay? In this case, I want to access the x data attribute of myself, and I want to subtract the x data attribute of this other coordinate. Square that, same for y, square that, and then add those and take the square root of that. So notice this method is pretty much like a function, right? You have def, some name, it takes in parameters, it does some stuff, and then it returns a value. The only difference is the fact that you have a self here as the first thing, and the fact that you always have to be conscious about whose data attributes you're accessing. Okay? So you have to use the dot notation in order to decide whose data attributes you want to access. So we've defined the method here, distance. Okay? So this is in the class definition. Now how do we use it? So let's assume that the definition of distance is up here. I didn't include the code. But really all you need to know is what it takes. It takes a self and an other. So when you want to use this method to figure out a distance between 2 coordinate objects, this is how you do it. So the first line, I create 1 coordinate object. Second line, I create another coordinate object. Right? First one is named C, the second one is named 0. These are 2 separate objects. And I'm going to find the distance. And I want to first call it on one object. So I'm going to say c dot. So I'm using the dot notation to call the method distance on object c. So Python says this object c is of type coordinate. It's going to look up at the class coordinate that you defined. It's going to find this method called distance. And then it's going to say, what parameters does it take? So it takes another parameter, right, for the other. And then in the parentheses, I just have to give it this other parameter. An easier way to see what happens is by looking at what this line here is equivalent to. Okay? So the third line here, print c.distance 0, is equivalent to this one on the right. And this one on the right essentially says, what's the name of the class? Dot notation. What's the method you want to call? And then in parentheses, you give it all of the variables, including self. Okay? So in this case, you're explicitly telling Python that self is c and other is 0. Right? So this is a little bit easier to understand, like that. But it's a little cumbersome, because you always have to write coordinate dot, coordinate dot, coordinate dot for every data attribute you might want to access, for every procedural attribute you might want to access. So it's a really, so by convention, it's a lot easier to do the one on the left. And as I mentioned, Python implicitly says if you're doing the one on the left, you can call this method on a particular object, and it's going to look up the type of the object, and it's going to essentially convert this on the left to the one on the right. Okay? And this is what you've been using so far. So when you create a list, you say L is equal to 1, 2, and then you say L dot append 3 or whatever. So we've been using this notation on the left pretty much from the beginning of class. So we have a coordinate class. We can create a coordinate object. We can get the distance between two objects. As you're using the class, if you wanted to use this coordinate class and you were maybe debugging at some point, a lot of you probably use print as a debug statement, right? And maybe you want to print the value of a coordinate object. So if you create a coordinate object, c is equal to coordinate 3, 4, right? That's what we've done so far. If you print c, you get this funny message. Very uninformative, right? It basically says, well, c is an object of type coordinate at this memory location in the computer, which is not what you wanted at all, right? Maybe you wanted to know what the values for x and y were. That would be a lot more informative. Okay? So by default, when you create your own type, when you print the object of that type, Python tells you this sort of information, which is not what you want. So what you need to do is you need to define your own method that tells Python what to do when you call print on an object of this type. Okay? So this is going to be a special method, just like init is, because it starts and ends with double underscores. Okay? And the name of the method is __str___. And if you define this method in your class, that tells Python, hey, when you see a print statement that's on an object of type coordinate, call this method. Look what it does, and do everything that's inside it. Okay? And you can choose whatever you can choose to make it do whatever you want inside your definition of str. Okay? In this case, let's say when we print a coordinate object, we're going to print its x and y values surrounded by angle brackets. That seems reasonable, right? So then, from now on, when you print coordinate objects, you're going to see things like this, which is a lot more informative. All right, so how do we define this? So far, we've defined all that, and the last part's going to be new. Okay? So we've defined the init and the distance, and let's define this str. So __str__ is a method. It's only going to take self because you're just calling print on the object itself. Okay? There's no other parameters to it. str has to return a string. And in this particular case, we're going to return the string that's the angle brackets concatenated with the x value of the object, self.x, concatenated with a comma, concatenated with the y value of this particular instance of an object, self.y, and then concatenated with the angle brackets. Okay? So now anytime you have print on an object of type coordinate, you're going to call this special method str if it's implemented in your code. Any questions? Okay. So let's try to wrap our hand around types and classes, because we've seen a lot today. Okay? Let's create a coordinate object, assign it 3, 4, as we have been, and assign it to variable c. We've implemented the str method, so when we print c, it's going to print out this nice 3, 4 in angle brackets. If we print the type of c, this is actually going to give us class main coordinate, which tells us that c is going to be an object c is going to be an object that is of type class coordinate. If we look at coordinate as a class, if we print what coordinate is a class, right? So this is what Python tells us. If we print coordinate, it's a class named coordinate. And if we print the type of a coordinate, well, that's just going to be a type. So class is going to be a type. So you're defining the type of an object. Okay? If you'd like to figure out if you'd like to figure out whether a particular object is an instance of a particular class, you use this special function called isInstance. So if you print isInstance c, coordinate, this is going to print true because c is an object that is of type coordinate. Okay. Couple more words on these special operators. So these special operators allow you to customize your classes, which can add some cool functionality to them. So these special operators are going to be things like addition, subtraction, using the equal sign, greater than, less than, length, and so on and so on. So just like str, if you implement any of these in your classes, this is going to tell Python. So for example, if we've implemented this __add __ in our class, this is going to tell Python when you use this plus operator between two objects of type coordinate to call this method. If you have not implemented this method and you try to add two objects of type coordinate, you're going to get an error because Python doesn't actually know right off the bat how to add two coordinate objects, right? You have to tell it how to do that. And you tell it how to do that by implementing this special method. Same with subtract, same with equal, so if you want to figure out whether two objects are equal. And when you implement these methods in your own class, you can decide exactly what you want to do. So what happens when you add two coordinate objects? Do you just add the x values? Do you just add the y values? Do you add them both together? Do you do whatever you'd like to do? And then you document what you've decided. So let's create a fraction object. Okay, so we've looked at a coordinate. We saw sort of a higher level car object. Let's look at a fraction object. Fraction object is going to represent a number that's going to be a numerator slash a denominator. Okay, so that's going to be a fraction object. So the way I've decided to internally represent a fraction object is with two numbers. And I've decided that I will not let them be floats. They have to be integers, hence the assert over here. So inside the init, I've decided I'm going to represent the two numbers with, I'm going to represent my fraction with two numbers, one for the numerator and one for the denominator. So when I create a fraction object, I'm going to pass in a numerator and a denominator. And a particular instance is going to have self.numerator and self.denominator as its data attributes, and I'm assigning those to be whatever's passed into my init. Since I plan on debugging this code, maybe possibly sometime in the future, I'm also including an str method. And the str method is going to print a nice, a nice looking string that's going to represent the numerator, and then a slash, and then the denominator. And then I've also implemented some other special methods. How do I add two fractions? How do I subtract two fractions? And how do I convert a fraction to a float? Okay? The add and subtract are almost the same, so let's look at the add for the moment. How do we add two fractions? Right? We're going to take self, which is the instance of an object that I want to do the add operation on. And we're going to take other, which is the other instance of an object that I want to do the operation on, so the addition. And I'm going to figure out the new top, so the new top of the resulting fraction. So it's my numerator multiplied by the other denominator plus my denominator multiplied by the other numerator, and then divided by the multiplication of the two denominators. So the top is going to be that. The bottom is going to be that. Notice that we're using self dot. Right? Once again, we're trying to access the data attributes of each different instance, right? Of myself and the other object that I'm working with. So that's why I have to do self dot here. Once I figure out the top and the bottom of the addition, I'm going to return. And here, notice I'm returning a fraction object. Okay? It's not a number, it's not a float, it's not an integer. It's a new object that is of the exact same type as the class that I'm implementing. Okay? So as it's the same type of object, then on the return value, I can do all of the exact same operations that I can do on a regular fraction object. Okay? Sub is going to be the same. I'm returning a fraction object. Float is just going to do the division for me. So it's going to take the numerator and then divide it by the denominator. Just divide the numbers. And then I'm defining here my own function, my own method called inverse. And this is just going to take the inverse of the instance I'm calling this method on. And so it's going to also return a new fraction object that just has the denominator as the top part and the numerator as the bottom part. So then we have some code here. So that's how I implement my fraction object. So now let's use it and see what it gives us. A is equal to fraction 1/4. This is going to be this is going to be 1/4 for A. And B is going to be 3/4. When I do C, notice I'm using the plus operator between two fraction objects, right? A and B are fraction objects. So Python's going to say, okay, is there an __add __ method implemented? It is. And it's just going to do whatever is inside here. So it's going to say self.numerator plus other.denominator. It's going to calculate the top and the bottom. It's going to return a new fraction object. So this is going to be 4 plus 4 divided by, 4 plus 12 divided by 16. Okay? And 16/16. So C as a fraction object is going to be 16 for the numerator and 16 for the denominator, right? Because it's a fraction object. If I print C, it should print 16/16, so we can even run it. So it prints 16/16. If I print float C, so this special method float here is going to say, is there a method that converts a fraction to a float? And there is. It's this one implemented right here. So it's just going to divide the two numbers, top and bottom, which gives me 1. So it's this one here. And here, notice I'm doing the exact same method call, except I'm doing it the other way, where you type in the name of the name of the class, name of the method, and then what you're calling it on. And this gives the exact same value here, 1.0. And then here I'm calling the method inverse on object B, which is going to invert 3 over 4 to be 4 over 3. And then I'm converting it to a float. And then I'm printing the value. So it gives me 1.33. Okay. So take a look at this. Take a look at this code in more detail, and see if you can trace through all of those different things, and see if you can also write your own new fraction objects. Okay. So last slide. The power of object-oriented programming is that you can bundle together objects that are of the exact same type. And all of these objects, are going to have the same data representation and the same methods that you can do on them. And ultimately, you're going to be building these layers of abstraction. So you're going to be building on a basic object type in Python. You're going to have integer objects, float objects. On top of those, you can create lists, dictionaries, and on top of those, you can even create your own object types, as we saw in this lecture from today.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So which of the following is a good and valid definition for a class representing a car? Okay, most of the people I think have gotten it, which is the red, which says class car object. And that's perfect. Okay? So this defines a function, this defines a class correctly, but A is just not descriptive name at all. And this is kind of weird, and this is the right one here.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
We have this definition for the class object. I've created the init for you. And here I'm giving it self, which is the first thing that you have to give it, and then 2 parameters, W and D. And for an instance of a car, I'm going to assign the data attribute named wheels to whatever is passed in for W. So notice that they're not the same name. And the data attribute for doors is going to be the value that's passed in for D. And also notice that inside the init, I can do any other sort of initializations that I'd like. So it's not just assigning variables from the parameters to variables for my objects. So in this case, I'm creating a new data attribute named color, and I'm going to just create it to be an empty string. Okay, notice because even though I didn't pass in any color to my object. So the question says, using the class definition above, which line creates a new car object with 4 wheels and 2 doors? Okay? So this first one is not right because it's trying to call the class with a variable, my car, so for self, which isn't quite right. So when you're creating your object, you have to give it 1 less parameter than what you have. So here, we're just going to have to create it with the W and the D. So we're going to create this variable my car, and we're going to assign it 4 for the number of wheels and 2 for the number of doors. And the number of wheels is the first parameter, and the number of doors is the second one. So it should be this one here, car 4, 2. So that's this one. Perfect.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So we're given this definition for car. We saw that on the previous slide. I want to add a method that's going to change the color of the car. And these are my four choices. And it looks like you guys are getting it right, which is awesome. Okay. So define a method to change the color of the car, which does this. So we know that self has to be the first parameter. So we can automatically eliminate A and C, and it's between B and D. And remember I said you have to be conscious about whose data attribute you're accessing. And in this case, we want to change the color of a particular instance of the car, right? So we have to say self.color instead of just color. If we just said color, then color would refer to just a variable inside the class, not a data attribute of a particular object.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
This is my definition, including the method to paint the car, so to change its color. And the question says you create a car with this line here. So you're initializing it with 4, 2. What's a line of code that changes the color from whatever initially is to red? The first one, car.paintRed, is sort of attempting to do the way that we saw on the right in the slides, where you're calling the class name dot, but it's missing the self. So we don't know what object to call it on. So that one's out of the running. The second one is closer, but we have red here as a variable as opposed to a string. So that one's not going to work. The third one looks good. And the fourth one is just weird. I don't think that one will work. It's attempting to put a value for self, but you've already called my car dot instead of the class name dot. So here, this isn't going to work. So since you already called the object name dot method name, you just have to give it the other parameter that it needs, which is the color. Okay? And I think the majority have gotten it right.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
OK. We have our class. We've done pretty much everything up until here. And we're going to add this special function here. So we're implementing this underscore, underscore, EQ, underscore, underscore. And implementing this is going to allow us to compare two types of cars. So the way I've decided to compare two types of cars is I'm saying, the two cars are going to be equal if they have the same number of wheels, they have the same color, and if they have the same number of doors. Okay? So if all of these are equal, then return true, and else return false. Inside the actual program here, I'm creating one car, 4 wheels, 2 doors. I'm changing its color to red. I'm creating another car, 4 wheels, 2 doors. By default, this new car, or your car, is going to have the color empty string, because that's how a new car gets initialized, right? So between my car and your car, the difference is going to be the color. Okay? So the color is not going to be the same. They have the same number of wheels and the same number of doors. So because I implemented the equal method in my code, this does not throw an error. This lets me proceed. It compares 4 with 4, which is good, 2 with 2, which is good, and then the colors don't match. So it's going to say false, which most of you guys are getting it right.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, everyone, let's get started. So today is going to be the second lecture on object-oriented programming. So just a quick recap of last time. On Monday, we were introduced to this idea of object-oriented programming, and we saw these things called abstract data types. And these abstract data types we implemented through Python classes. And they allowed us to create our own data types that sort of abstracted a general object of our choosing, right? So we've used lists before, for example, but with abstract data types, we were able to create objects that were of our own types. We saw the coordinate example, and then at the end of the class, we saw the fraction example. So today, we're going to talk a little bit more about object-oriented programming in classes. We're going to see a few more examples, and we're going to talk about a few other nuances of classes, talk about information hiding, and class variables. And then in the second half of the lecture, we're going to talk about the idea of inheritance. So we're going to use object-oriented programming to sort of simulate how real life works. So in real life, you have inheritance, and in object-oriented programming, you can also simulate that. OK, so the first few slides are going to be a little bit of a recap, just to make sure that everyone's on the same page before I introduce a couple of new concepts related to classes. So recall that when, in the last lecture, we talked about writing code from 2 different perspectives, right? The first was from someone who wanted to implement a class. So implementing the class meant defining your own object type. So you defined the object type when you defined the class. And then you decided what data attributes you wanted to define your object. So what data makes up the object? What is the object? Okay. In addition to data attributes, we also saw these things called methods. And methods were ways to tell someone how to use your data type. So what are ways that someone can interact with the data type? Okay. So that's from the point of view of someone who wants to write their own object type. So you're implementing a class. And the other perspective was to write code from the point of view of someone who wanted to use a class that was already written. Okay? So this involved creating instances of objects. So you're using the object type. Once you created instances of objects, you're able to do operations on them. So you're able to see what methods whoever implemented the class added, and then you can use those methods in order to do operations with your instances. So just looking at the coordinate example we saw last time, a little bit more in detail about what that meant. So we had a class definition of an object type, which included deciding what the class name was. And the class name basically told Python what type of an object this was. Okay? In this case, we decided we wanted to name a coordinate. We wanted to create a coordinate object, and the type of this object was therefore going to be a coordinate. We defined the class in a sort of general way. Okay? So we needed a way to be able to access data attributes of any instance. So we used this self variable. Okay? And the self variable was we used to refer to any instance, to the data attributes of any instance in a sort of general way without actually having a particular instance in mind. Okay? So whenever we access data attributes, we would say something like self dot. To access a data attribute, you'd access the attribute directly with self.x. Or if you wanted to access a method, you would say self dot and then the method name, for example, distance. And really the bottom line of the class definition is that your class defines all of the data, so data attributes, and all of the methods that are going to be common across all of the instances. So any instance that you create of a particular object type, that instance is going to have this exact same structure. Okay? The difference is that every instance's values are going to be different. So when you're creating instances of classes, you can create more than one instance of the same class. So we can create a coordinate object here using this syntax right here. So you say the type and then whatever values it takes in. And you can create more than one coordinate object. Each coordinate object is going to have different data attributes. It's going to have different data attribute values. Okay? Every coordinate object is going to have an x value and a y value. But the x and y values among different instances are going to vary. Okay? So that's the difference between defining a class and looking at a particular instance of class. So instances have the structure of the class. So for a coordinate, all instances have an x value and a y value. But the actual values are going to vary between the different instances. Okay, so ultimately, why do we want to use object-oriented programming? So far, the examples that we've seen are were numerical, right? A coordinate, a fraction. But using object-oriented programming, you can create objects that mimic real life. So if I wanted to create objects of an object that defined a cat and an object that defined a rabbit, I could do that with object-oriented programming. I would just have to decide as a programmer what data and what methods I'd want to assign to these groups of objects. Okay? So using object-oriented programming, each one of these is considered a different object. And as a different object, I can decide that a cat is going to have a name, an age, and maybe a color associated with it. And these three here on the right, each one of these rabbits is also an object. And I'm going to decide that I'm going to represent a rabbit by just an age and a color. Okay? And with object-oriented programming, using these attributes, I can sort of group these three objects together and these three objects together. Okay? So I'm grouping sets of objects that are going to have the same attributes together. And attributes, this is also a recap of last time, come in two forms, right? Data attributes and procedural attributes. So the data attributes are basically things like, that define what the object is. So how do you represent a cat as an object? And it's up to you as a programmer to decide how you want to do that. For coordinate, it was pretty straightforward. You had an x and a y value. If we're representing something more abstract like an animal, then maybe I would say, well, I'm going to represent an animal by an age and a name. Okay, so it's really up to you to decide how you want to represent, what data attributes you want to have to represent your object with. Procedural attributes were also known as methods. And the methods are essentially asking, what can your object do? Okay, so how can someone who wants to use your object, how can someone interact with it? So for a coordinate, we saw that you can find the distance between two coordinates. Maybe for a more abstract animal object, you might have it make a sound, okay, by maybe printing to the screen or something like that. Okay, this slide's also a recap of how to create a class, just to make sure everyone's on the same page before we go on. So we defined a class using this class keyword, and we said class, the name of the class. So now we're going to create a more abstract animal class. We're going to see in the second half of the lecture what it means to put something else in the parentheses, but for now we say that an animal is an object in Python. So that means it's going to have all of the properties that any other object in Python has. And as we're creating this animal, we're going to define how to create an instance of this class. So we say def, and this init was the special method that told Python how to create an object. Inside the parentheses, remember we have the self, which is a variable that we use to refer to any instance of the class. Okay, we don't have a particular instance in mind. We just want to be able to refer to any instance. Okay, so we use this self variable. And then the second parameter here is going to represent what other data we use to initialize our object with. So in this case, I'm going to say I'm going to initialize an animal object with an age. Okay, so when I create an animal, I need to give it an age. Inside the init are any initializations that I want to make. So the first thing is I'm going to assign an instance variable age. So this is going to be the data attribute age to be whatever is passed in. And then I'm also making another assignment here where I'm assigning the data attribute name to be none originally. Later on in the code, when I want to create an animal object, I say the class name, and then I pass it in whatever parameters it takes, in this case the age. And I'm assigning it to this instance here. Okay? All right. So now we have this class animal. We've done the first part here, which is to initialize the class, right? So we've told Python how to create an object of this type. There's a few other methods here that I've implemented. Next two we call getters, and the two after that we call setters. Okay? And getters and setters are very commonly used when implementing a class. So getters essentially return the values of any of the data attributes. Okay? So if you look carefully, getAge is just returning self.age, and getName just returns self.name. So they're very simple methods. Similarly, setAge and setName, we're going to see what this funny equal sign is doing here in the next couple of slides. But setters do a very similar thing where they're going to set the data attributes to whatever is passed in. Okay? So those are getters and setters, and then the last thing down here is this str method, and this str method is used to tell Python how to print an object of this type animal. So if you didn't have this str method, if you remember from last lecture, what ends up happening is you're going to get some message when you print your object that says this is an object of type animal at this memory location, which is very uninformative, right? So you implement this method here, which tells Python how to print an object of this type. Okay? So the big point of this slide is that you should be using getters and setters. You should be implementing getters and setters for your classes. And we're going to see in the next couple of slides why exactly. But basically, they're going to prevent bugs from coming into play later on if someone decides to change the implementation. So we saw how to, so the previous slide, this slide here, shows the implementation of the animal class. And here we can see how we can create an instance of this object. So we can say A is equal to animal3. So this is going to create a new animal object with an age of 3. And we can access the object through the variable A. Dot notation, recall, is a way for you to access data attributes and methods of a class. Okay? So you can say A.age, later on in your program, and that is allowed. It'll try to access the age data attribute of this particular instance of the class A. So this is going to give you 3. However, it's actually not recommended to access data attributes directly. So this is the reason, so you're going to see in the next slide, the reason why we're going to use getters and setters. Instead, you should use the getAgeGetter method to get the age of the animal. So this is going to return also 3. So these are going to do the same thing. And the reason why you'd want to use getters and setters is this idea of information hiding. Okay, so the whole reason why we're using classes in object-oriented programming is so that you can abstract certain data from the user. Okay, one of the things you should be abstracting is these data attributes. So users shouldn't really need to know how a class is implemented. They should just know how to use the class. Okay? So consider the following case. Let's say whoever wrote the animal class wants to change the implementation. And they've decided they don't want to call the data attribute age anymore. They want to call it years. Okay? So when they initialize an animal, they say self.years is equal to age. So an animal still gets initialized by its age, and the age gets passed into a data attribute named years. Okay? Since I'm implementing this class, I want to have a getter which is going to return self.years. So I'm not returning self.age anymore because age is no longer the data attribute I'm using. So with this new implementation, if someone was using this implementation and was accessing age directly as accessing the data attribute age directly, with this new implementation, they'd actually get an error, right? Because this animal that they created using my old implementation no longer has an attribute named age. And so Python's going to spit out an error saying no attribute found or something like that. Okay? If they were using the getter a.getAge, the person who implemented the class re-implemented getAge to work correctly, right, with their new data attribute years as opposed to age. So if I was using the getter getAge, I wouldn't have run into the bug. Okay? So things to remember: write getters and setters for your classes, and later on in your code, use getters and setters to prevent bugs and to promote easy-to-maintain code. Okay. So information hiding is great, but having said that, Python's actually not very great at information hiding. Okay? Python allows you to do certain things that you should never be doing. Okay. So the first we've just seen. So the first is to access data attributes from outside of the class. Okay? So if I were to say a.age, Python allows me to do that without using a getter and setter. Python also allows you to write to data attributes from outside the class. So if I implemented the class animal, assuming that age was a number, an integer, and all of my methods work as long as age is an integer, but someone decided to be smart and outside of the class set age to be infinite as a string, that might cause the code to crash. Okay? Python allows you to do that, but now you're breaking the fact that age has to be an integer, right? So now the methods should probably be checking the fact that age is an integer all the time. The other thing that you're allowed to do is to create data attributes outside of the class definition. Okay? So if I wanted to create a new data attribute called size for this particular instance, Python also allows me to do that. And I can set it to whatever I want. Okay? So Python allows you to do all these things, but it's actually not good style to do any of them. So just don't do it. All right. So the last thing I want to mention, the last thing about classes before we go on to inheritance, is this idea called default arguments. And default arguments are passed into methods. And since methods are functions, you can also pass in default arguments to functions. So for example, this setName method had self, and then this new name is equal to this empty string here. Okay? We haven't seen this before. But this is called a default argument. And you can use the function in one of two ways. The first way is, so we can create a new instance of an animal type object with this line here, a is equal to animal3. And then we can say a.setName. So this calls the setter method to set the name. And notice we've always said that you have to put in parameters for everything other than self, okay? But here we have no parameters passed in. But that's okay, because new name actually has a default argument, okay? So that tells Python if no parameters passed in for this particular formal parameter, then use whatever is up here by default. So if I haven't passed in the parameter a.setName, a.setName is going to be setting the name to the empty string, because that's what the default parameter is. So in the next line, when I print a.getName, this is just going to print the empty string, okay? If you do want to pass in a parameter, you can do so as normal. So you can say is equal to animal3, a.setName, and then pass in a parameter here. And then new name is going to be assigned to whatever parameters passed in, like that. Whatever you pass in overrides the default argument, and everything is good. So when I print a.getName, this is going to print out the name that you've passed in. Questions about default? Yeah. What if you don't provide a default value for new name? If you don't provide a default argument for new name and you do this case here, then that's going to give you an error. So Python's going to say something like expected one argument got 0 or something like that. Great question. Okay. All right, so let's move on to this idea of hierarchies. Okay? So the great thing about object-oriented programming is that it allows us to add layers of abstraction to our code. Right? So we don't need to know how very, very low-level things are implemented in order to use them, and we can build up our code to be more and more complex as we use up these different abstractions. So consider every one of these things on this slide as being a separate object. Right? Every one of these things can be considered to be an animal. Okay? According to our implementation of an animal, the one thing that an animal has is an age. Okay? And that's probably true, right? Every one of these things has an age. But now I want to build up on this and create separate groups, right? And each one of these separate groups that I create on top of animal is going to have its own functionality, right? They're going to be a little bit more specific, a little more specialized. So I can create these 3 groups now, a cat, a rabbit, and a person group. And for example, so they're all animals, right? They all have an age. But for example, maybe a person's going to have a list of friends, whereas a cat and a rabbit do not. Maybe a cat has a data attribute for the number of lives they have left, right? Whereas a person and a rabbit do not, okay? So you can think of adding these more specialized, adding functionality to each one of these subgroups, okay? So they're going to be more and more specialized, but all of them retaining the fact that they are animals. So they all have an age, for example. So on top of these, we can add another layer and say that a student is a person and is an animal, okay? But in addition to having an age and maybe also having a list of friends, a student might also have a major, or they're pretty young, so maybe their favorite subject in school. So that's the general idea of hierarchies. Okay? So we can sort of abstract the previous slide into this one and say that we have parent classes and child classes. Okay? The animal class is like our parent class. It's the highest level class. Inheriting from the animal class, we have these child classes or subclasses. Okay? Whatever an animal can do, a person can do. Whatever an animal can do, a cat can do, and whatever an animal can do, a rabbit can do. Okay? That is, have an age and maybe some really basic functionality. Okay? But between person, cat, and rabbit, they're going to be varying wildly as to the kinds of things that they can do, right? But they can all do whatever animal can do. So child classes inherit all of the data attributes and all of the methods or behaviors that their parents' classes have. Okay? But child classes can add more information. Like, for example, a person can have a list of friends, whereas a general animal will not. It can add more behavior, like maybe a cat can climb trees, whereas people and rabbits cannot. Or you can also override behavior. So in the previous one, we had animal, person, student. So maybe we have an animal doesn't speak at all, but a person can speak. So that's added functionality to the person. And maybe a person can only say hello, but then when we talk to a student, we can override the speak method of a person and say that a student can say, I have homework or I need sleep or something like that. Okay? So we have the same speak method for both person and student because they can both speak, but student will override the fact that they say hello with something else. Okay, so let's look at some code to put this into perspective. So we have this animal class, which we've seen before. This is the parent class. Okay? It inherits from object, which means that everything that a basic object can do in Python, an animal can do, which is things like binding variables, very low-level things. Okay? We've seen the init, we've seen the two getters, the setters, and the string method to print an object of type animal. All right, now let's create a subclass of animal. We'll call it cat. Okay? We create a class named cat. In parentheses, instead of putting object, we now put animal. And this tells Python that cat's parent class is animal, so everything that an animal can do, a cat can do. So that includes all of the attributes, which was age and name, and all of the methods. So all the getters, the setters, the str, the init, everything that the animal had, now the cat has, the cat class has. In the cat class, we're going to add two more methods, though. Okay, the first is speak. So speak is going to be a method that's going to just take in the self, okay? No other parameters. And all it's doing is printing meow to the screen. Very simple. Okay? So through this speak, we've added new functionality to the class. So an animal couldn't speak, whereas a cat says meow. Additionally, through this str method here, we're overriding the animal str. Okay? So if we go back to the previous slide, we can see that the animal's str had animal plus the name plus the age here. Whereas the cat's str now says cat, name, and the age. Okay? So this is just how I chose to implement this. Okay? So here I've overridden the str method of the animal class. Notice that this class doesn't have an init, and that's okay, because Python's actually going to say, well, if there's no init in this particular class, then look to my parents and say, do my parents have an init? Okay? And if so, use that init. So that's actually true for any other methods. So the idea here is, when you have hierarchies, you have a parent class, you have a child class, you can have a child class to that child class, and so on and so on. So you can have multiple levels of inheritance. What happens when you create an object that is of type something of a type that's the child class of a child class of a child class, right? What happens when you call a method on that object? Well, Python's going to say, does a method with that name exist in my current class definition? And if so, use that. But if not, then look to my parents. Do my parents know how to do that? Right? Do my parents have a method for whatever I want to do? If so, use that. If not, look to their parents, and so on and so on. So you're sort of tracing back up your ancestry to figure out if you can do this method or not. So let's look at a slightly more complicated example. We have a class named person. It's going to inherit from animal. Inside this person, I'm going to create an init method. And the init method is going to do something different than what the animal's init method is doing. It's going to take in self as usual, and it's going to take in 2 parameters as opposed to 1, a name and an age. First thing the init method's doing is it's calling the animal's init method. Why am I doing that? Well, I could theoretically initialize the name and the age data attributes that animal initializes in this method. But I'm using the fact that I've already written code that initializes those 2 data attributes. So why not just use it? Okay? So here this says, I'm going to call the class animal. I'm going to call its init method. And I'm going to leave it up to you to, not you as the class, but I'm talking to as the program is running. I'm going to leave it up to you to figure out how to initialize an animal with this particular age and what to name it. So Python says, yep, I know how to do this, so I'm going to go ahead and do that for you. So now it says person is an animal, and I've initialized the age and the name for you. The next thing I'm doing in the init is I'm going to set the name to whatever name was passed in. Okay? So in the init, notice I can do whatever I want, including calling methods. And then the last thing I'm doing here is I'm going to create a new data attribute for a person, which is a list of friends. Okay? So an animal didn't have a list of friends, but a person is going to. The next 4 methods here are, this one's a getter, so it's going to return the list of friends. This is going to append a friend to the end of my list. I want to make a note that I actually didn't write a method to remove friends, so once you get a friend, they're friends for life. But that's okay. The next method here is speak, which is going to print hello to the screen. And the last method here is going to get the age difference between 2 people, so that just basically subtracts their age and says it's a 5-year age difference or whatever it is. And down here I have an str method which I've overridden from the animal, which instead of animal : name, it's going to say person : name : age. Okay? So we can run this code. So that's down here. I have an animal, person here. So I'm going to run this code. And what did I do? I created a new person. I gave it a name and an age. I created another person, a name and an age. And here I've just run some methods on it, which was get name, get age, get name, get age for each of the 2 people. So that printed Jack is 30, Jill is 25. If I print P1, this is going to use the str method of person, so it's going to print person : their name and then their age. P1.speak just says hello, and then the age difference between P1 and P2 is just 5. So that's just subtracting and then printing that out to the screen. Okay, so that's my person. Let's add another class. This class is going to be a student, and it's going to be a subclass of person. Since it's a subclass of person, a student is going to inherit all the attributes of a person, and therefore all the attributes of an animal. The init method of a student is going to be a little different from the one of a person. We're going to give it a name, an age, and a major. Notice we're using default arguments here. So if I create a student without giving it a major, the major is going to be set to none originally. Once again, this line here, person.init self-name age, tells Python, hey, you already know how to initialize a person for me with this name and this age, so can you just do that? And Python says, yes, I can do that for you. And so that saves you maybe like 5 lines of code just by calling the init method that you've already written through person. Okay? So student has been initialized to be a person. And additionally, we're going to set another data attribute for the student to be the major, and we're going to set the major to be none. The student is going to get this setter here, the setter method, which is going to change the major to whatever else they want if they want to change it. And then I'm going to override the speak method. So the speak method for the person, recall, just said hello. A student is going to be a little bit more complex. I'm going to use the fact that someone created this random class. Okay? So this is where we can write more interesting code by reusing code that other people have written. So someone wrote a random class that can do cool things with random numbers. So if I want to use random numbers in my code, I'm going to put this import random at the top of my code, which essentially brings in all of the methods from the random class. One of the methods being this random method. So random open close parentheses is a random method from the random class. And this essentially gives me a number between 0 and 1, including 0, but not including 1. Okay? So this random number I get here is going to help me write my method for speak, where it's going to, with 25% probability, it's either going to say I have homework, I need sleep, I should eat, or I'm watching TV. Okay? So a student is going to say one of those 4 things. And the last thing I'm doing down here is overriding the str method. So let's look at the code. I'm going to comment this part out and uncomment the student and see what we get. Okay, so here I'm creating the student. I'm creating one student whose major is CS, name is Alice, and age is 20. S2 is going to be another student, name Beth, age 18, and the major is going to be none because I didn't pass in any major here. So by default, using the default argument, it's going to be none. If I print S1, S2, that's going to print out these 2 things over here, just by whatever str method does. And then I'm going to get the students to speak. And if I run it multiple times, you can see that it's going to print different things each time. So I need sleep, I have homework, I need sleep, I have homework. Yeah. So every time it's going to print something different. Okay. Questions about inheritance in this example? Okay. Last thing we're going to talk about in this class is an idea of, or in this lecture, is the idea of a class variable. Okay? So to illustrate this, I'm going to create yet another subclass of my animal called a rabbit. So class variables, so far we've seen, sorry, let me back up. So far we've seen instance variables, right? So things like self.name, self.age, those are all instance variables. So they're variables that are specific, they are common across all of the instances of the class, right? Every instance of the class has this particular variable. But the value of the variable is going to be different between all of the different instances. So class variables are going to be variables whose values are shared between all of the instances in the class. So if one instance of the class modifies this class variable, then any other instance of the class is going to see the modified value. So it's sort of shared among all of the different instances. So we're going to use class variables to keep track of rabbits. Okay, so we're creating this class rabbit. Tag is equal to 1. We haven't seen something like this before. So tag is our class variable. Class variables are typically defined inside the class definition, but outside of the init. So tag is going to be a class variable, and I'm initializing it to 1. Inside the init, this tells us how to create a rabbit object. So I'm going to give it self as usual, an age, and then 2 parents. Don't worry about the 2 parents for now. Inside the init, I'm going to call the init of the animal because, just to do less work, Python already knows how to initialize an animal for me, so let's do that. So that's going to set the 2 data attributes, name and age. I'm going to set the data attributes for parent 1, parent 2 for a rabbit to be whatever's passed in. And then this is where I'm going to use this class variable. So I'm creating this data attribute, instance variable, particular to a specific instance, called RID. Okay? And I'm assigning this instance variable to the class variable. And I access class variables using not self, but the class name. So in this case, rabbit.tag. So initially, tag is going to be 1. And then the init is going to increment the tag by 1 here. Okay? So that means that from now on, if I create any other instances, the other instances are going to be accessing the updated value of tag instead of being 1. So let's do a quick drawing to show you what I mean. So let's say I have rabbit.tag here. Okay? So initially, tag is going to be 1. Okay? And then I'm going to create a new rabbit object. So this is as I'm calling the code. Okay? So let's say this is a rabbit object. Oh boy. Okay. R1. You know, I actually Googled how to draw a rabbit, but that didn't help at all. Okay. So R1 is going to be a new rabbit that we create. Initially, what happens is when I first create this new rabbit, it's going to access the class variable, which its current value is 1. So when I create the rabbit ID, r1.rid, this is going to get the value 1. And according to the code, after I set the rabbit ID to whatever tag is, I'm going to increment the tag. So this is going to say, OK, now that I've set it, I'm going to go back up here and increment the tag to be 2. OK. So let's say I create another rabbit object. OK. All right. There. That's a sad rabbit. R2. The ID of R2 is going to be what? Well, according to the way we create a new rabbit object is it's going to access whatever the value of tag is, which is a class variable. It was changed by the previous creation of my rabbit, so now I'm going to access that, right? So the value is going to be 2. And according to the code, the next thing I do after I create the instance RID is I'm going to increment tag. So I'm incrementing the class variable to be 3. Okay? So notice that all of my instances are accessing this shared sort of resource, the shared variable called tag. So as I'm creating more and more rabbits, they're all going to be incrementing the value of tag because it's shared among all of the instances. And so this tag class variable sort of keeps track of how many different instances of rabbits I've created throughout my entire program. Okay? So the big idea here is that class variables are shared across all of the instances, so they can all modify them. But these RIDs, right, these instance variables, are only for that particular instance. So R2 can't have access to R1's ID value, nor it could change it, but it won't change it across all of the different instances. Okay. So that's how the init method works of rabbit. Okay? So we have these tags that keep track of how many rabbits we've created. We have a couple of we have some getters here to get all the parents. So now let's add a somewhat more interesting function. Oh, I just want to mention, when I'm getting the RID, I'm actually using this cool zfill function here, or method, which actually pads the beginning of any number with however many zeros in order to get to that number here. So the number 1 becomes 001 and so on. So it ensures that I have this nice looking sort of ID type thing that's always 3 digits long. So let's try to work with this rabbit object. Let's define what happens when you add 2 rabbits together, okay? In this class, not in the real world. Okay. So if I want to use the plus operator between 2 rabbit instances, I have to implement this __add __ method. Okay? So all I'm doing here is I'm returning a new rabbit object. Okay? Whoops, sorry about that. And let's recall the init method of the rabbit. Okay? So when I'm returning a new rabbit object, I'm returning a new rabbit object that's going to have an age of 0. self, so the rabbit object I'm calling this method on is going to be the parent of the new rabbit, and other is going to be the other parent of the new rabbit. Okay? So if we look at the code, and I run it, this part here, I'm creating 3 rabbits, R1, R2, and R3. Notice this class variable is working as expected because the IDs of each of my rabbits increments as I create more rabbits. So we have 001, 002, 003. If I print R1 and R2 and R3, that was these 3 lines over here. The parents of R1 and R2 are none because that's just the default arguments for creating a rabbit. To add 2 rabbits together, I use the plus operator between 2 rabbit objects. And on the right here, I'm testing rabbit addition. And I can print out the IDs of all my rabbits. And notice that when I've created this new rabbit R4, the ID of it still kept incrementing. So now the ID of the 4th rabbit is 004. And then when I get R4's parents, they are as we want them to be, so R1 and R2. The other thing I want to do is to compare 2 rabbits. So if I want to compare 2 rabbits, I want to make sure that their parents are the same. So I can compare the parent, the first parent of the first rabbit with the first parent of the second rabbit, and the first parent of the second parent of the first rabbit to the second parent of the second rabbit, or getting the combinations of those 2. So that's what these 2 Booleans are doing. So these are going to tell me, these are going to be Boolean values, either true or false, and I'm going to return either they have the same parents of that type or the same parents crisscrossed. Okay? So here, notice that I'm actually comparing the IDs of the rabbits as opposed to the rabbit objects directly. Okay? So if instead of comparing the IDs in here, I was comparing the parents themselves directly, what would end up happening is this function, this method EQ, would get called over and over again because here we have parents that are rabbits. And at some point, the parents of the very, very first rabbits ever created by this program are none. And so when I try to call, the parent 1 of none, that's going to give me an error. Okay? Something like an attribute error where none doesn't have this parent attribute. Okay? So that's why I'm comparing IDs here. Okay? And the code in the lecture here shows you some tests about whether rabbits have the same parents. And I've created new rabbits here, R3 and R4, the addition of those 2. And R5 and R6 are going to have the same parents down here, true, but R4 and R6 don't. Okay? So just to wrap it up, object-oriented programming is the idea of creating your own collections of data where you can organize the information in a very consistent manner. So every single type of object that you create of this particular type that you create, every object instance of a particular type is going to have the exact same data attributes and the exact same methods. Okay? So this really comes back to the idea of decomposition and abstraction in programming. All right, thanks everyone.